Hi there and welcome to this new video. In this video we talk about binary exploitation, and specifically in this video I want to go over some of the most important memory protection mechanisms. Why is it important to understand the protection mechanism? Well, if you want to do binary exploitation, at some point you will need to bypass this mechanism. Therefore, it is really crucial that you understand how they work and why they were introduced. So in this video, we will see a bunch of this memory protection, such as the following four. We will analyze what they do and why they were introduced. As always, I hope the video is interesting and you get something out of it. If you do, subscribe to the channel, and if you choose, you can also support me on Patreon. Thank you very much for your support and enjoy the video. So let's start off with talking about memory protection. So in order to mitigate certain binary exploitation techniques, various mechanisms have been implemented over the years. Now in this video we will see the following four: non-executable memory, stack canaries, address space layout randomization, and position independent executables. Now there are more, but these are one of the core ones, I would say. So let's start off with non-executable memory, which is also known as NX or DAP. So NX stands for no execute, which is also known as DEP, data execution prevention. And it is a memory protection mechanism that marks certain areas of memory to be not executable. Now, if a memory page is marked as non-executable, it means that code cannot run from that page. It is only readable and writable, but it cannot be executed. Now, why is this important? Now, this kind of protection is extremely useful. It is especially useful when it is applied to critical areas of memory where the user input might be saved, such as the stack, the heap, and other data sections. Why is this the case? Well, in security, remember, anytime we deal with user input, we might be dealing with malicious user input. For example, the earliest attack on memory like stack-based buffer overflows, how did they work? Well, basically, you had this buffer overflow into the stack. So you have this stack, and within this stack, you use the buffer overflow to write within the stack a shellcode. And then execution, you force the CPU to jump into the shellcode that you just introduced. Now this means that the CPU at some point was fetching instruction from the stack. It was executing data taken from the stack. This was a very vulnerable pattern, a very dangerous pattern, and so they introduced the idea of like, okay, let's mark certain section of memory to be not executable. Why? Because ultimately, I know that only the text section should be executable. Everything else can be not executable, can be marked with the NX bit. And this is of course especially true for the stack. Now consider a very simple C binary that is vulnerable to buffer overflow. Like this, we have an input of 64 characters, but in the input of the user, we read up to 500. So clearly we're gonna put 500 into 64 and it's gonna overflow. Pretty simple. Now the cool thing is that, look, here we have this, this vul.c is the code that I just showed. Pretty simple code. Now when we automatically compile such binary, here we're gonna get some warning for the buffer overflow, but we don't really care about that. That's not the focus at this point. The focus is this: is the stack executable or not if we compile by default a binary? And the answer is that yes, by default the stack is not executable. Now, how can we actually check that? We can use the readelf utility. Now, readelf, of course, because the binary is of elf format. Elf is the binary format in Linux system, and we can do as follows. We can do readelf. We're gonna grep for this particular value, stack, and look at this. Here we see RW, read write. We do not see the execute. In this case, read write means that the stack is not executable. If we want to compile a program whose stack is executable, and remember, this is a security risk, we can do it as follows. We're gonna introduce the -z flag with exec stack. So we do the same, but now if you do the readelf once again, notice this, we get the executable bit. So here we get the E bit, E letter more, which means executable. So we can read, we can write, we can execute it. Now, why would you do this? To be honest, I don't really suggest you do this. After all, it is a security risk. By default, the stack is not executable, and to be honest, it really shouldn't be unless you are working with some really specific condition and context, which is probably dangerous on its own. There's no point for the stack to be executable, and if the stack is executable, essentially, you are giving the attacker a very powerful attack vector, because now we can just put any code into the stack, shellcode any sort of like things into the stack, and then he can execute it. So this is really not good. So you should avoid having the stack executable, because after all, the attacker has not only has control over the stack in most cases, but the stack follows a very simple functioning. So it's not really too hard to set up the stack in a certain way. Of course, the same thing can be done with the heap, but with the heap it's much harder to manage it and to attack it. So the first protection that we saw was that, okay, let's mark a certain memory region to be not executable. Like, okay, this one is executable, this one is not, so it has the NX, this one is not, the NX, and stuff like this. This is useful to avoid the attacker being able to load custom code into the memory and then execute it later on. Okay, at this point we can talk about the second protection mechanism, which are the stack canaries. Now, stack canaries are a runtime protection mechanism designed to detect and prevent stack buffer overflows. What is the canary? The canary is a random value, and it is a random value that is placed just before the return address on the stack when a function is called. When a buffer overflow happens, before overwriting the saved return address, the canary saved in the stack will also be modified. So basically here the idea is as follows. Within the stack frame of the function, at the end, we find the saved return address. So saved return address. Okay, now the canary works as follows. In a buffer overflow, the situation is that, okay, you're gonna write a lot of bytes here, and it's gonna overflow, and then you're gonna overflow the saved return address. So to detect such overflows, what the canary does is, okay, let's place a value before the saved return address. Let's call it the canary, and let's put this with a random value. I don't know, like 7F, A, C, D, whatever. Now, when you overflow, if you modify the canary, and you're gonna modify the canary if you overflow, and if you change the value of the canary in any sort of way, the execution, the CPU, will actually recognize this. There's gonna be a check in code that makes sure that before you leave a function, before you take the save return address and you follow it up through execution, you actually make sure that the canary has not changed. If you change even a single byte of the canary, execution will abort. So that's basically the idea. The system will notice this change and will interrupt the execution of the program. So here we have a different program. Once again, very simple. We have a main that calls hello. Hello simply calls like what's your name, and here we have the buffer overflow. But once again, I'm not really exploiting anything in this video. I'm just showcasing protection mechanism. So can compile it as follows. So let's first compile it without canary. So here I have my code, canary.c, nothing special. Let's compile this thing without canary. So look at this, let's compile this without canary. We get once again the warnings for the buffer overflow, and let's analyze it with the GDB. So I'm gonna do this. I'm actually gonna do this with GDB-q canary. Okay. So the first thing that we want to do is actually let's put it. I'm gonna put it down. So the first thing I want to do is I want to put a breakpoint at hello plus 47. Why hello plus 47? Because if I disass the hello function, 47 happens right after the f gets. So right after we read the user input. So let's put a breakpoint there. Then I'm gonna run and I'm gonna put this pattern. I mean, this pattern it's nothing special. It's just so that we can see clearly in memory in terms of hex bytes. So I'm gonna put this, I have the breakpoint, perfect. Now at this point, I can grab some values from the RSP, so from the stack. So look, this is the top of the stack at this point. Here is my user input, of course, that ends in these last bytes. Perfect. Okay, so now what do we do here? Well, the cool thing is that we have to wonder where is the saved return address among these bytes. And actually we can do that easily by doing info frame. So info frame is going to tell us a bunch of information regarding the current frame, and specifically we have these save registers RIP at, and it's going to give us the address of the saved return address for this current frame. So it's going to say RIP at this address. Now this address is basically this cell. So this address is pointing to this cell. Why? Well, because the 7FFFE400 begins here, but then you have 8 bytes for this value, and so like the 8 here starts here basically. So this is the value we are interested in. Also, another way to look at it is hello is called from main. Like, remember the code here, hello, this one is called from main. Now if you just do a this as main, notice the call hello here, and then we have this CE, right? This is the next instruction after the call to hello. And notice that in the stack here, this value is exactly as this value. So it is the next instruction. So yeah, we did find the saved return address. Perfect. Now, another thing that is saved is the value of the previous RBP, of the RBP of the previous stack frame, because as I already made some videos about stack frames, but the idea is that they are built on top of each other. So anytime here you save the RBP for the previous one, for the one down in the hierarchy. So that's good. But basically this is it. We just have the data itself of the user, the saved RBP, and the saved return address. In this case, there is no canary. There is no extra value that we don't know. This is also because notice that this space, the space that exists between the starting of the user input and essentially the saved RBP is exactly 64 bytes. And here I write it more clearly. I have essentially memory used for the array input, this array of this range of memory, saved RBP and saved RIP, so saved return address. So that's basically the idea. And this was an execution without canary. Remember, we removed the canary. Let's compile it normally now. And when you compile it normally, this protection mechanism is enabled by default. So when you compile normally, the canary is enabled by default. Once again, let's debug it. So this time the situation is a little bit different, because if we do this as hello, notice that now we have this stack check fail. So we have a new function, and this function is actually gonna abort execution when the canary check does not work. So it's a little bit different. We have a little bit more code. So this time we put a breakpoint in hello plus 62, because this time 62 is the one after the fcats. Then we do run, we put this input, and then we extract some bytes from the stack, once again RSP, and we do info frame. Now let's analyze this situation. So this is the top of the stack, and this info frame is telling us that we have RBP and RIP saved, right? So the saved return address is this one once again. The saved RBP is this one instead, is at 400. So saved return address 408, saved RBP 400. Now notice that from before something changes. Because now, yes, we do have still the user input up here, but now there is a third value that was not there between the saved registers and the user input. Now this value, this one is the canary. This one is the canary, basically. So that's the idea. This one is the canary, and if we modify something, when we do a buffer overflow, what's gonna happen is that we're gonna modify these bytes, then modify these bytes, and these bytes, and this byte, and this byte, and these bytes. At some point, we're gonna modify the canary, and if the CPU recognizes that this change has happened, it's gonna abort execution. And it's gonna abort execution by executing the function check fail, like basically this one, stack check fail. And you can actually see this difference in code too. Like, look at this. Without canary, the code is up here. With canary, the code is slightly different. Specifically, what changes here, if you analyze it, here we have some loading here, basically, that has to do with this one, these instructions that were not there. And then at the end of the flow, here, after this, before the NOP, actually after the NOP here, we have all this thing. Before we had NOP leave ret, we have NOP, then we have this block, which had to do with the canary. So these two things at the top and at the bottom have to do with the canary. They were introduced by the compiler automatically to insert a canary in the stack frame, which is a very useful thing to do. And this function, stack check fail, essentially just prints out a message like stack smashing detected, pretty much. And you can see this in the standard glibc implementation. It's just a way to abort the program and write a message. And so this is it with respect to the canary memory protection. When you think of the canary, think of this. Between the user input and the save registers and the saved return address, there is a random value. If anyone changes, if anyone touches such random value, the processor will recognize the change and will abort execution to prevent further hijacking of the program. So the third memory protection mechanism is called Address Space Layout Randomization, abbreviated as ASLR. So this one is a security technique used to protect binaries such as executable files and library files against corruption vulnerabilities and exploitation attempts. Basically, the idea is that there is a randomization of key data areas and structures, including the base address of the executable, the stack, the heap, and shared libraries, such as the libc that is automatically inserted into the execution. So basically, with ASLR, every time the program runs, its memory layout is different. And you can actually see that in practice by using the LDD command, because LDD lists out all the shared libraries that are loaded when you execute the program, and it gives you the base address on which they are loaded. So for example, notice this, libc.6. So in this first run, it ends with A000. In the second run, it's different because now, okay, this initial part is the same, but everything else is different. And the third time, same thing. Initial part is same, but everything else is different. So basically, every time you load the binary, you have different sections. You have the same memory, but it's loaded in different section of the actual process memory. Now, with respect to randomization, you can also randomize the code itself, the section that contains the executable code. However, if you want to randomize that, you have to make a position independent executable, that is a pi executable. Otherwise, the code section will not be randomized. But we will talk about that in a little bit. So why is randomizing an address a security strategy? Why does it increase security? Well, because many exploits that have to do with memory corruption or with general like logic vulnerabilities, they actually target specific data or code in memory. And this data or code must be properly addressed within the exploit. For example, ROP attacks, where ROP stands for return-oriented programming, these kind of attacks are characterized because they use small pieces of legitimate code found within the binary, and these are called gadgets, to actually construct an exploit. So basically they hijack the execution of the binary and they make the binary do things that it was not supposed to do by using code that is already found within the binary. These are very fascinating attacks that we will see in a little bit in future videos. So basically, to actually perform such an attack, you need to target these specific snippets of codes, these specific gadgets. You need their addresses. Now, how do you deal with ASLR? How can you work with it? Well, basically, you can configure it with a kernel parameter. And the kernel parameter of interest is found in /proc/sys/kernel/randomize via space. So when you're dealing with the Linux kernel, you have these files, these special files that actually allow you to communicate with the kernel. And this one is one such file. So, for example, if I just check my file, it's gonna say true. It's gonna have the value true. Why true? Because true means full randomization. It randomizes all segments, and of course, if you have a pi executable, also the code sections. But you can also have the value 0 and 1. So 1 is for partial randomization, which means that the code will not be randomized, only like the data and the other stuff like secondary sections. And with 0, it's actually fully disabled, which of course, once again, is a security risk. there is no need for you to disable it unless you're working with a very specific environment, which is gonna be weird anyways. So how can you work with it, or how can you change the parameter? Well, for example, you can do like this. So you can do echo with the value you want, and then t, which is gonna write it into this particular file. So for example, just to showcase in this video, I just did it down the shell, and now if I actually do, like, look at this, so I just did it. So like if I do cat once again, it's gonna be 0. Now if I do once again LDD of canary, look at this address, 95000, right? I do it again, 95000. And the same applies to the other libraries as well. Now everything is static. Now everything is loaded in the same exact address. This means that the attacker can easily understand the memory location through a little bit of brute forcing, and can just use those hard-coded section within the exploit, and it's gonna be much easier to craft the exploit, of course. Now I've activated it again, it's true once again, and if I do canary, look at this, it's gonna be 10000, and it's gonna change. Now it changes again. So you can either disable it for the entire system, which is much more risky, and I do not recommend it unless you're testing out some exploit, but be careful to enable it back again. And also, if you're testing out some exploit, maybe you want to do it in a virtual machine, which is better. But you can also disable it for the current shell with the set arc command. So let's see, for example. Now, as I said, in this shell now, things work properly because it is properly randomized, right? Perfect. But now, if I do this set arc, and then I do LDD canary, notice that once again, things are fixed. So they do not change. Why they do not change? Because I removed the randomization, but only for this shell. If I open a new shell, like terminal 2, and I do the same thing, right? Canary. Once again, notice I have the randomization. So the cool thing about this command is that it allows you to experiment with a specific shell without compromising the entire system. And so this is good. One final note is that ASLR works at the level of user space. It is a user space protection mechanism. However, of course, when we're dealing with any operating system, we always have different levels of abstractions, and specifically we have the user space and we have the kernel space, which interacts, of course, with the devices itself, right? With the firmware of the devices. But basically the idea is that, okay, we have randomization for the user through ASLR, but there is also randomization for the kernel. It's just called in a different way. It's called KASLR. Kernel address space layout randomization, and this one is used to randomize the base address where the Linux kernel is loaded into memory, and it also affects where the modules are loaded, where the stacks of the kernel are used, and some kernel data structures. Of course, the more random, the better security, but at the same time, the code itself needs to have some structure, so you have to be careful with how you introduce randomness into the application. But the basic idea is that why is randomness a security strategy? Because now the people who want to exploit us, the exploit, have to first understand where things are placed into memory and then exploit them. So there is a level of complexity, of added complexity, because not everything is in the same place, and this creates more like it's gonna be more difficult to exploit. So the final protection mechanism that I want to talk about is PI, Position Independent Executable. So this is more like a useful configuration to have. Basically, a PI binary is a binary that is compiled in a way that it allows it to be loaded at any memory address. So if you want to implement full ASLR, you need, of course, to also randomize the memory pages which contain the code sections, and this can only be done if you have a PI binary. Without PI, the text segment of a binary will stay at a fixed address, which makes it easier, of course, for attacker to use ROP gadgets when it comes to return-oriented programming. Now, to compile a binary as PI, what you have to do is this thing. You have to do gcc fpi pi and then the TPL compilation, and don't worry, this happens by default. So, for example, let's take once again the vulnerable vul.c. Extremely simple C file. So if I compile it as PI like this, then I can check if actually I have a PI as follows. Look at this, dyn, position independent executable file. I can also check out with file vuln. It's going to be pi executable. That's what we want, position independent executable file. Now we can actually test the effect of having a pi executable as follows. We can use GDB. Now GDB by default actually disables randomization. So we need to enable it again. We just want a normal working binary like it would totally execute on the system without GDB. And we can do that with the set disable randomization off. So we just do this, and then we can just put a breakpoint in main, we can run, and look at the address. So this is the address that we have. So this 5551D. Then we quit and we do it again. So put break in main and then we execute it. Notice that actually here the address is the same. Okay, why is this the same? Because probably in this shell we had disabled the ASLR. Exactly. So I'm gonna remove this, I'm gonna create a new shell, and I'm gonna do it again, basically. So the address was the same before because we had disabled randomization in that context. So wait a second, is this now disabled or not? Okay, now it seems to like work properly. Fine. We have a pi executable, but we have to do this. Okay, perfect. We'll put breakpoint in main and I run. Look at this address. Seems pretty random to me. So this is the first address that we saw. I'm gonna put it here. Let's do it again. So I'm gonna create GDB. I'm gonna break in main. I'm gonna start it. Look at this. We have a different address. So we have a different address. It is loaded in a different place. So this essentially is the effect of having pi. Every time you execute, not only you randomize the data section, you also randomize the code. And this makes it even harder to use ROP gadgets, for example, to use return-oriented programming techniques to exploit your binary. So finally, how can we exploit a binary as a non-pi? So we're just gonna execute it as follows. Actually, let's do it like this. So I'm gonna execute it like this, no pi. If I do a file right now, it's not gonna say pi executable, it's just gonna say executable, and also I can check it as follows. It's gonna say exec executable file. Before it actually said dyn, position independent executable file, so it's slightly different. So basically this is the same. Now if I do the same exercise as before, so I like enable randomization with GDB, I put a break in main and I execute, I get this address, so let's put it here. Here is with pi, and here is without pi. And then I quit, and I do it again. Break main, run. Notice that I get the same address for main. Because without pi, I cannot randomize the address of the executable itself, of the code itself that runs. And I think this is good to just add it to the note. They're gonna be available for those of you who support me on Patreon. So final results with pi, without pi. Basically, that's the idea. Now, how can you quickly understand this kind of configuration of a binary? Like if it has stack not executable, if it has a canary and things of the sort. Well, you can actually use a Checksec. It's a pretty simple program. You can install it in Arch Linux as follows. And the way you use it is just to Checksec. So let's run here. Do Checksec file vuln. And it's going to give you a bunch of information. Like, look at this. It's going to say, look, stack canary found, NX enable, no pi, no path, and stuff like that. So this is basically the idea. Now, to finish off the video, is this enough? Are these protection enough? And of course, the answer is not really. While each protection mechanism reduces the risk for exploitation because it makes it harder to exploit a binary, it is still possible to find a way to bypass this mechanism and exploit the target. For example, if you cannot put code into the stack, you can use other techniques such as ROP or ret to libc. These techniques aim not to introduce new malicious code, but to use the existing code that is already present in the binary in a malicious way. So they are trying just to use what is already there, but in a malicious way. With the stack canaries, for example, you can leak the value of the canary, and if you know the value of the canary in your exploit, when you overflow the stack, you can put back the right canary so that the processor does not realize a buffer overflow happened, because the true protection of the canary only happens when you cannot predict the canary itself. If you can predict it, you can also write it once again into the stack, and essentially you are bypassing that kind of defense. For ASLR, you can have memory leak. For position independent executable, you can have address leaks. So basically the idea is that randomization can be, you can defeat randomization if you are able to leak specific addresses. And in the future videos of this series, when we talk about binary exploitation, we will see such examples of simple exploits that use these techniques. So this is it for this video. I hope it was fun, I hope it was interesting, I hope you got something out of it, and if you do, subscribe to the channel, and if you want, you can support me on Patreon. That's it, and to the next video.